this very moment, something built by human hands is still whispering to Earth from nearly 24 billion kilometers away. It is older than the internet, farther than every planet, and so distant that its faint radio signal takes almost an entire day to arrive. And somehow, across that freezing black gulf, Voyager 1 is still telling us what exists at the edge of our sun's domain. That matters because Voyager 1 is not just a machine drifting into darkness. It is our most distant outpost, a tiny working witness in a place no human being has ever seen up close. By the end of this, you will understand what it is still transmitting, how we are even able to hear it at all, what those ghostly signals reveal about the boundary of our solar system, and why this lonely spacecraft has become one of the strangest and most moving scientific conversations in history. And if you genuinely enjoy space stories told this way, with the mystery first and the explanation right behind it, give the video a like and subscribe. It really helps the channel, and it tells me you want more deep dives like this. And down in the comments, tell me where you are watching from, and answer this. If you could send one short message into interstellar space, what would you say? Because Voyager 1, in its own way, is still answering that question for us. To really feel what that means, it helps to go back to the beginning. Not to deep space, but to Earth in the late 1970s, when a machine was launched on what was supposed to be a planetary tour and somehow became our first active presence between the stars. What can a spacecraft still say when it is farther away than almost anything we have ever made? What does space even become when you are no longer really inside the solar system, but not fully beyond its influence either? What kind of environment surrounds Voyager 1 now? And how can a machine designed decades ago still survive there? And perhaps most haunting of all, when its signals finally stop, what exactly will humanity lose? Voyager 1 launched on September 5th, 1977. It was not the first of the two Voyager spacecraft to leave Earth, despite its name. Voyager 2 launched first, but Voyager 1 took a faster path. Its job, at first, was focused and ambitious, but still recognizably finite. Visit Jupiter, visit Saturn, send back images and measurements, transform tiny dots and blurred bands into real places, and it did that spectacularly. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980. Those encounters alone would have secured its place in history. At Jupiter, it helped reveal a world of violent storms and active geology. It captured the first close images of Ios volcanic eruptions, showing that even far from the sun, a moon could be geologically alive. At Saturn, it delivered stunning views of the rings and the thick, hazy atmosphere of Titan. Its flyby of Titan, in fact, was so scientifically valuable that mission planners deliberately aimed Voyager 1 onto a path that would prevent it from going on to Uranus and Neptune. That close pass bent its trajectory upward and out of the plane of the planets, and setting it on a one-way route toward the outer dark. In a sense, Voyager 1 completed its original mission decades ago. Everything after Saturn was the bonus mission. But bonus mission makes it sound casual, almost secondary. What followed was one of the most extraordinary scientific extensions ever attempted. Voyager 1 kept going, and because it kept going, it became the first spacecraft to approach the borderlands of the heliosphere, the enormous bubble inflated by the sun. To understand what Voyager 1 is transmitting today, you first have to understand where it is. The solar system is not just the planets. That is the first thing. When most of us picture the solar system, we imagine the sun at the center, the planets in their orbits, maybe the asteroid belt, maybe comets at the edge. But physically, the sun controls a much larger realm. Whilst it pours out a constant stream of charged particles called the solar wind. This wind is not like air moving through a sky. It is a flow of electrically charged matter, mostly protons and electrons, racing outward in all directions from the sun at hundreds of kilometers per second. For a long time, this wind dominates the local space environment. It carries the sun's magnetic field outward with it, stretching solar influence into a huge bubble called the heliosphere. Think of the heliosphere as a vast, invisible weather system generated by the sun, embedded inside the wider galaxy. Earth, Jupiter, Saturn, all the planets, all of them orbit inside this solar bubble. But the heliosphere is not permanent, and it is not smooth. It is pushing outward into interstellar space, and interstellar space pushes back. Outside the heliosphere lies the interstellar medium, the thin gas, dust, and magnetic fields that occupy the space between stars. It is incredibly sparse by Earth standards, far better than any vacuum chamber we can create in a laboratory. But on cosmic scales, it is still matter. And where the outward pressure of the solar wind meets the pressure of the interstellar medium, boundaries form. One of those boundaries is called the termination shock. This is the region where the solar wind, after racing outward faster than the speed at which disturbances can travel through that plasma, slows down abruptly. Beyond that lies the heliosheath, a turbulent outer layer where the slowed solar wind is compressed, heated, and redirected. Farther still is the heliopause, the boundary where the outward flow of solar material is finally stopped by the interstellar medium. Beyond the heliopause, interstellar space begins. That phrase sounds clean and decisive, but in reality, these borders are not like the edge of a table or the surface of water. They are dynamic, structured, and shaped by pressure, magnetism, solar activity, and motion through the galaxy. If you imagine Voyager 1 crossing some bright line painted in the dark, that is not what happened. There was no sign saying, "You are now leaving the solar system." There was a complicated shift in physical conditions, and scientists had to infer what it meant from the data. And those data are the heart of what Voyager 1 is still transmitting. Voyager 1 is astonishingly far away. Around 24 billion kilometers is a number so large that it resists intuition. Once light itself, moving at nearly 300,000 kilometers per second, takes roughly 22.5 hours to travel one way from Voyager 1 to Earth, depending on the exact distance at the time. If mission controllers send a command, they do not get a response the same day in the ordinary sense. There is a long silence built into every exchange. It is less like operating a machine and more like corresponding with a patient ghost. The spacecraft itself is not large. The main bus is about the size of a small car. A 3.7-meter high-gain antenna, its large dish, faces back toward Earth. Instruments sit on booms to reduce interference from the spacecraft's own electronics. A long boom holds the magnetometer. Another extends to help keep power systems at a manageable distance. It is a machine designed in an era of far less computing power than the phone in your pocket. Yet it was built with a kind of stripped-down robustness that now feels almost heroic. Voyager 1 is powered not by solar panels, but by radioisotope thermoelectric generators, often shortened to RTGs. Solar panels would be almost useless at this distance, because sunlight has become desperately weak. The intensity of sunlight falls with the square of the distance. Double the distance, and you get 1/4 the light. Out at Voyager's current range, the sun is still the brightest star in its sky, but as a source of usable power, it is feeble. So Voyager carries its own energy source, heat from the natural radioactive decay of plutonium-238, converted into electricity. That power source is reliable, but not eternal. Every year, the electrical power available to the spacecraft drops a little more. That slow decline has shaped the mission for decades. Engineers have had to turn instruments off one by one over time, not because the spacecraft reached a destination and stopped working, but because keeping anything alive that far from home becomes a ruthless accounting problem. Every watt matters. Every heater, every detector, every transmitter competes for survival. So when we ask what Voyager 1 is still transmitting, we are really asking two things at once. What science data is it still able to send back from interstellar space? And what engineering information is it still sending about itself, proof that the machine remains alive? The answer begins with its instruments. Voyager 1 no longer carries an active camera mission. In fact, its cameras were turned off long ago to save power. That means it is not sending back pictures of alien landscapes or glowing clouds in the dark. If you are imagining cinematic interstellar vistas, the reality is quieter and in some ways much stranger. Voyager 1 is sending numbers, tiny changes in voltage, counts of charged particles, measurements of magnetic fields, readouts of plasma behavior, telemetry about temperature, orientation, power use, and subsystem health. And from those numbers, scientists reconstruct an environment no human eye has ever seen. This is one of the deep themes of modern astronomy and space science. We often think discovery means seeing, but much of the universe is understood indirectly. A graph can be a landscape. A fluctuating radio count can be a weather report from the edge of the sun's influence. Voyager 1 is not a camera pointed into infinity. It is more like a weather station, a particle detector, and a survival beacon drifting through a frontier where the medium itself becomes the message. Among the instruments that have been crucial in recent decades are the cosmic ray subsystem, the magnetometer, the plasma wave system, and the low-energy charged particle instrument, though instrument availability and operation have changed as power has declined. Each of these sees a different aspect of the invisible environment around the spacecraft. The cosmic ray subsystem detects highly energetic particles, including those originating from outside the solar system. Cosmic rays are charged particles, mostly protons and atomic nuclei, and accelerated by powerful astrophysical events, such as supernova explosions and other energetic processes in the galaxy. The heliosphere partially shields the inner solar system from some of this galactic radiation. That means the farther you move toward the heliopause and beyond it, the more cosmic rays should appear. The low-energy charged particle instrument helps detect particles associated more directly with the solar wind and other energetic particle populations. If solar influence drops, these populations should change. The magnetometer measures the strength and direction of the local magnetic field, which can reveal whether Voyager is still embedded primarily in the solar magnetic environment or has entered a region dominated by the interstellar magnetic field. And the plasma wave system can detect oscillations in the surrounding plasma, effectively allowing scientists to infer the density of the ionized gas around the spacecraft. That last one turned out to be especially important. For years, one of the great scientific dramas surrounding Voyager 1 was the question of whether it had actually left the heliosphere. People often remember a single announcement date, but the reality was more subtle and more interesting. Around 2012, Voyager 1 began detecting dramatic changes. The intensity of lower energy particles associated with the heliosphere dropped sharply. At the same time, galactic cosmic rays increased. It looked very much as though the spacecraft had entered a new region. Many expected a clear rotation in the magnetic field direction as well, a kind of magnetic signpost that interstellar space had been reached. But that clear change did not immediately appear in the way many had expected. So scientists hesitated. Had Voyager entered a transitional zone, a magnetic highway, a layer where particles behaved differently, but the field still aligned in a surprising way? Had it crossed the Heliopause or only approached it? The mystery was real. This was not a public relations cliffhanger. It was a genuine scientific puzzle, because no one had ever sampled this region directly before. Then the plasma wave data helped solve it. Voyager 1 does not have a working instrument designed to directly measure the bulk flow of plasma in that region anymore, which complicated matters. But when a solar eruption from the Sun traveled outward and eventually passed by Voyager, it caused oscillations in the surrounding plasma. The plasma wave system detected those oscillations, and from their frequency, scientists could infer the local electron density. That density was much higher than expected for the heliosheath, and much more consistent with the interstellar medium. It was like hearing the echo in a dark room and realizing the walls are much closer or much farther than you thought. The medium around Voyager had changed. By combining that clue with the particle data, scientists concluded that Voyager 1 had crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. So, one of the most important things Voyager 1 is still transmitting is evidence about the physical character of the local interstellar medium. Not some abstract and distant interstellar medium inferred from telescopes looking across light years, but the actual environment our spacecraft is moving through right now, sample by sample, pulse by pulse. That alone is extraordinary. Imagine standing on a shoreline in dense fog. You cannot see the ocean. You cannot see the land behind you. But you can feel the wind change, hear the texture of the waves, smell salt replacing Earth. Voyager 1 did something like that on a cosmic scale. It did not send us a dramatic photograph of the boundary. It sent us subtle shifts in particle counts and plasma density. Yet those shifts told us that the Sun's great protective bubble, enormous beyond ordinary human imagination, still has an edge. And that edge can be crossed. The phrase interstellar space can sound as though Voyager 1 has escaped the solar system entirely, and Sirius. But this is where language needs care. In one sense, yes, it has entered interstellar space because it is beyond the Heliopause, beyond the region where the solar wind dominates. But in another sense, it is still deeply within the Sun's gravitational reach. If you define the solar system by gravitational influence and by populations of distant icy bodies, then Voyager 1 has an unimaginably long way to go. It will take more than 300 years just to reach the inner edge of the hypothetical Oort cloud, if that estimate is used, and tens of thousands of years to pass through it completely if the cloud extends as many models suggest. So Voyager 1 is in interstellar space, but not beyond the broader solar system in every possible definition. It is a reminder that nature rarely obeys our simple labels, and boundaries depend on what property you are measuring. Plasma environment, magnetic dominance, gravitational influence, orbital populations, all of these can define an edge, and those edges do not all coincide. What is Voyager 1 actually transmitting today, in practical terms? First, it transmits engineering telemetry. This is the spacecraft talking about itself. How much power is available? What the temperatures are in various components? Whether thrusters are functioning? How systems are configured? Whether the spacecraft is maintaining the proper orientation? The dish antenna must remain pointed toward Earth with astonishing accuracy. A tiny misalignment over such a distance can be the difference between communication and silence. That means attitude control, the ability to know and adjust orientation, is everything. Voyager 1 uses small thrusters to maintain this orientation. Over the years, even this became a story of ingenuity. Some thrusters degraded. Engineers revived backup thrusters that had been dormant for decades. Imagine bringing an old machine back to life from across billions of kilometers, knowing your command will travel for nearly a day before it arrives, then waiting nearly another day to know whether it worked. It is a form of engineering patience, almost impossible to imagine in everyday life. No quick troubleshooting, no real-time joystick, just physics, planning, and hope. Telemetry matters because without it, the science data are almost meaningless. If you do not know the spacecraft's state, you cannot interpret its instruments properly. A temperature drift, a power fluctuation, a pointing issue, or a data system fault can create confusion that looks like science, but is really hardware. So Voyager's self-reporting is the first layer of what it transmits. I am here. I am powered. I am stable enough to listen and speak. Second, it transmits measurements of energetic particles. These help scientists study how the heliosphere modulates cosmic rays and how that changes beyond the heliopause. Inside the heliosphere, the solar wind and solar magnetic field help deflect and slow some incoming galactic cosmic rays. Beyond the heliopause, that shielding weakens dramatically. Voyager 1 has recorded higher levels of cosmic rays than spacecraft inside the heliosphere typically experience. That is scientifically valuable, not only because it reveals the nature of the boundary, but because cosmic radiation is one of the great hazards of deep space exploration. If human beings ever travel far beyond Earth orbit for long periods, perhaps to Mars, and eventually much farther, radiation will be one of the central problems to solve. Cosmic rays are not just space is dangerous in some vague cinematic sense. They are high-energy particles that can damage electronics, degrade materials, and harm living tissue. Voyager 1 is effectively sampling the radiation environment of a more exposed cosmic neighborhood. It is not giving us the full answer for crewed interstellar travel, which remains vastly beyond current capability, but it is giving us direct evidence of what lies outside the Sun's shielding bubble. Third, Voyager 1 transmits data about magnetic fields. Magnetism in space is subtle but fundamental, and charged particles do not move freely without regard to fields. They spiral, drift, and interact according to magnetic structures. By measuring the magnetic field around it, Voyager helps scientists understand how the heliosphere interacts with the local interstellar magnetic field. This tells us about the shape of the heliopause, the degree of coupling across the boundary, and the broader question of how stars carve cavities in the galaxy around themselves. This matters beyond our own sun. Every star with a wind likely creates some version of an astrosphere, a bubble around itself. If we want to understand how stellar systems interact with interstellar space, and how cosmic rays penetrate those systems, and how planetary environments are influenced by their wider galactic setting, the Voyager measurements become a kind of reference point. One star, one crossing, one direct dataset, but immensely valuable. Fourth, Voyager 1 transmits plasma wave data that allow scientists to infer plasma density in the local interstellar medium. That may sound esoteric, but it is one of the closest things we have to placing a sensor directly in the matter between stars. Interstellar space is not empty in the everyday sense. It contains atoms, ions, magnetic fields, and cosmic dust spread over vast distances. The density is extremely low, but not zero. The heliosphere has its own plasma character, and the interstellar medium has another. Measuring the density, changes over time, can reveal structure in the medium, disturbances propagating outward from the sun, and the texture of the environment on scales no telescope can probe in exactly the same way. This is one of the eerie beauties of Voyager 1. It reveals that the frontier between our space and the galaxy is not just an abstract concept. It has measurable density, it has pressure, it has waves, it can ring when struck by a solar eruption. It has a physical reality. There is also the transmission itself, the radio link, which is a marvel in its own right. Voyager 1 sends its data using a transmitter whose power output is tiny by modern broadcasting standards. By the time that signal spreads across nearly 24 billion kilometers, it reaches Earth unimaginably weak. The received power is often described in terms so small they almost stop sounding real. Detecting it requires the Deep Space Network, the global system of giant radio antennas operated by NASA, with complexes in California, Spain, and Australia spaced around Earth, so that at least one can track distant spacecraft as the planet rotates. Picture the signal leaving Voyager 1 as a narrow radio beam aimed back toward Earth. Even with the high-gain antenna, by the time it arrives, that energy has spread enormously. It is less like someone speaking across a room, and more like trying to detect the heat of a candle from across a continent, though even that comparison is too generous in some ways. The Deep Space Network uses massive dishes, sensitive receivers, and careful signal processing to pull that whisper out of the background noise of the universe and our own technology. And remember, this is not a quiet environment. Earth is drenched in radio interference from human civilization and natural sources. Deep space communication requires precision. The network must know where Voyager is, how fast it is moving relative to Earth, what frequency shifts will result from that motion, how the spacecraft is oriented, and how to separate its transmission from everything else. It is an act of listening so delicate that it borders on the poetic. That alone would make Voyager 1 remarkable. But the story becomes even stranger when you consider that the spacecraft has had serious communication and data problems in recent years. Aging spacecraft do not fail in neat ways. Components drift. Software behavior becomes harder to interpret. Hardware degrades in combinations no one can fully simulate. In 2023 and 2024, for example, engineers dealt with a major anomaly involving the flight data system, one of the computers responsible for packaging, science, and engineering data. Voyager 1 remained in contact, but it was returning unreadable or unusable data. It was like hearing a familiar voice from the dark, suddenly speaking in fragments and static. The challenge was immense. You are trying to diagnose a 1970s spacecraft at interstellar distance, with long communication delays, limited power, no physical access, and incomplete ability to reset or reconfigure systems without risk. Engineers had to investigate memory corruption, data pathways, and possible workarounds. They could not simply reboot everything and see what happens. A wrong move could end the mission. What happened next was one of those moments that makes the Voyager story feel almost impossible. Our engineers identified a likely memory problem and began carefully shifting code and data to other parts of memory, essentially performing remote surgery on an elderly interstellar spacecraft from Earth. Over time, they recovered meaningful engineering data, then science data, bringing parts of Voyager 1's voice back into coherence. When people say Voyager is still transmitting, this is part of what that means. Not just that the transmitter is on, but that there is an active human effort to preserve intelligible contact with a machine launched when disco was new, while it moves through a region no spacecraft had ever explored before. There is an entire invisible relationship embedded in that phrase. Voyager speaks, Earth listens, Earth responds. Days pass between one sentence and the next. The spacecraft is also still carrying the golden record, and that fact tends to hover over every discussion of Voyager 1 like a second, quieter mission. The golden record is not part of what Voyager is transmitting by radio, of course. It is a physical artifact attached to the spacecraft, a phonograph record containing sounds, music, greetings, and images encoded for any possible finder in the distant future. In practical scientific terms, the golden record is not why Voyager matters today. It is not how we learn from the mission. But emotionally and symbolically, it changes the whole texture of the story. Voyager 1 is both an instrument and a message in a bottle. One part of it faces inward, toward Earth, still returning data. Another part faces outward, toward deep time. The radio transmission is the living conversation. The golden record is the fossil of a civilization hoping to be remembered. Still, if we stay grounded in the science, what Voyager is telling us right now is more than enough to justify the awe. One of the most important things the mission has done is show that the Heliopause is not a simple, static shell. Data from Voyager suggest a more textured interaction between solar and interstellar plasmas than many simplified diagrams imply. The magnetic field direction beyond the Heliopause was not as dramatically different as some had expected at the moment of crossing, which forced scientists to rethink assumptions about how those fields drape and connect near the boundary. In other words, Voyager did not just confirm old models. It complicated them, and that is often how real discovery works. This is easy to miss if you only hear the headline version. We like scientific stories that end with a clean answer. Did it leave the solar system? Yes. Done. But the richer truth is that when Voyager reached the edge, it did not merely place a check mark beside a prediction. It found a boundary that was physically real but conceptually tricky. Particle intensities changed sharply. Plasma density indicated interstellar conditions. Yet the magnetic story was subtler. That tension was not failure. It was science happening in real time. Voyager 1 has also helped reveal that the interstellar medium itself is not uniform. There appear to be variations in density and conditions as the spacecraft moves outward. Some of these changes can be detected when shock waves or disturbances from solar activity eventually catch up with it, compressing the local plasma and producing wave signatures. That means the Sun, despite being far behind Voyager now, in a practical sense, can still send influence into the region around it. A solar eruption on the Sun can race outward for months or years and eventually pass the spacecraft, triggering measurable effects in interstellar plasma. This is a staggering thought if you slow down enough to feel it. The Sun is not just a bright disk in the sky. It is an active star whose violence can echo through tens of billions of kilometers. A disturbance born in the solar atmosphere can travel outward, cross the planetary realm, pass the Heliopause, and shake the plasma around a lonely spacecraft between the stars. The scale of cause and effect becomes almost hard to hold in the mind. Another thing Voyager 1 is still transmitting, indirectly, is information about time itself in a cosmic engineering sense. Its failing power supply, cooling systems, and instrument shutdowns are not just mission management details. They are a live demonstration of what endurance looks like in space. Spacecraft age differently from objects on Earth. There is no weather in the ordinary sense, no oxygen rusting metal, no liquid water freezing into cracks. But there is relentless radiation, thermal stress, mechanical fatigue, and the unforgiving absence of repair. Voyager is teaching us slowly what survives and what does not when human technology is asked to persist for half a century in deep space. Its motion is another part of the story. Voyager 1 is moving at roughly 17 kilometers per second relative to the Sun, though exact values vary depending on frame of reference and how one describes the trajectory. That is astonishingly fast by human standards. Faster than a rifle bullet by a huge margin. Fast enough to cross North America in minutes if you could somehow maintain that speed in the atmosphere, which you very much could not. And yet, on the scale of interstellar space, it is glacial. If Voyager 1 were aimed toward the nearest star system, Proxima Centauri, which it is not, it would still take tens of thousands of years to arrive. That is one of the humbling paradoxes it embodies. It is our fastest, farthest emissary, and even so, the stars remain almost impossibly far apart. Voyager does not make the universe feel smaller, it makes its vastness feel real. So what does the environment around Voyager 1 likely look like now? There is almost nothing to see in the cinematic sense. No glowing border wall, no dense star field suddenly appearing like a hyperspace reveal. Space remains mostly black because it is mostly empty. The sun from that distance would still be brighter than other stars, but reduced to a very intense star-like point, rather than a warm disk dominating a sky. The planets are all far behind, invisible without instruments. The spacecraft moves through a medium so thin that even gas almost sounds misleading. Yet physically, it is in a different ocean from the one it left. The particle populations have changed. The plasma density has changed. The balance of pressures has changed. The magnetic context has changed. Voyager 1 is sailing not through emptiness, but through another starless weather system, one belonging not to our sun, but to the local galaxy itself. That local interstellar medium has a history. The sun is moving through the Milky Way, and the region around us is shaped by ancient stellar events, possibly including old supernova explosions that helped carve the broader local bubble, a region of relatively low-density hot gas in which our solar system resides. The exact structure and history of these regions are subjects of ongoing research, but the point is this. The space around Voyager is not generic blankness. It is part of a dynamic galactic environment shaped by stars living and dying over millions of years. Voyager 1 is giving us a single in situ sample of that environment. One needle in one patch of the cosmic ocean. That may sound limited, and it is, but direct sampling matters. If all you had ever known of Earth's oceans came from looking at sunlight on the surface from orbit, the first thermometer lowered into the water would be revolutionary. Voyager is that lowered instrument. There is also a philosophical strangeness in the fact that so much of what Voyager transmits is invisible by nature. Humans evolved to understand the world through surfaces, sounds, motion, light. But Voyager's frontier is made of charge, field, density, radiation, and wave behavior. To grasp what it is telling us, we have to translate invisible quantities into understanding. We have to accept that reality is often structured by things no human sense can directly feel. In that way, Voyager is not only exploring deep space, but it is expanding the range of what counts as human perception. And then there is the question of how long this can continue. The answer is not forever, but longer than one might reasonably expect. Because its power supply steadily weakens, mission teams have had to make hard decisions for years, shutting down heaters and instruments to keep the core spacecraft and essential systems operating. The exact timeline changes depending on spacecraft condition, power performance, and engineering choices. But the general expectation has long been that some science operations could continue into the 2020s and perhaps beyond in reduced form. Eventually, though, there will not be enough electricity to power the instruments and transmitter together in a useful way. One by one, and the systems will go dark. It is worth pausing on how gentle that ending is likely to be. Voyager 1 is not expected to explode, crash, or dramatically vanish. It will probably fade. First one instrument, then another. More heaters off, tighter power budgets, increasing fragility. Finally, One day, perhaps after a command sequence succeeds, perhaps after a final telemetry frame arrives, there will be no more coherent response. The spacecraft will still exist. It will still be moving. The golden record will still be attached. But the conversation will have ended. At that point, Voyager 1 will become a silent object in interstellar space, no longer a functioning probe, but still an artifact of Earth traveling around the galaxy for millions of years, at least until some collision or slow physical degradation alters it beyond recognition. The chance of it ever being encountered by another civilization is extraordinarily small. Interstellar space is too vast, targets too tiny, timescales too long. The golden record is not a practical communication plan. It is a gesture. But what a gesture! Before that silence comes, though, every transmission still counts. Every usable data point from Voyager 1 now is precious, because there will never be another first crossing of the Heliopause by humanity. Voyager 2 has also crossed, and its data are invaluable because they give a second sampling point and reveal differences between locations in the heliosphere's boundary. But Voyager 1 was first, and it continues to probe conditions along its own path into interstellar space. Each additional year extends our baseline. Scientists can compare changing plasma density, magnetic conditions, and cosmic ray intensities over time. Patterns emerge that a shorter mission could never have revealed. Long baselines are a hidden superpower in space science. Some phenomena only become intelligible when watched for decades. Solar cycles rise and fall. The heliosphere expands and contracts. Disturbances propagate outward over years. A mission that survives long enough stops being just a snapshot and becomes a chronicle. Voyager 1 is not merely telling us where the boundary was, it is telling us how the boundary breathes. There is something almost biological in that idea. The heliosphere is not alive, but it pulses with the life of the sun. Solar activity changes its pressure. Shocks move through it. Particles wax and wane. Fields twist and reconnect. And Voyager, now beyond the boundary, can still sense the after effects when the sun coughs in its direction. We are watching our stars reach from the outside for the first time. This changes how you think about being inside the solar system. We tend to imagine Earth as circling the sun in some stable local arrangement, almost like a tidy diagram in a classroom. But in reality, Earth is inside a moving stellar bubble, carried through the galaxy by a star that emits a wind and magnetic field, carving out a cavity in the interstellar medium. The space around us is active. The sun is not just shining on the planets. It is creating an entire protective domain around them. Voyager 1 helps us feel that domain by leaving it. If all of this sounds abstract, it may help to ground it in a single human comparison. Picture the longest road trip imaginable. Except the car was built when your grandparents were young. The driver can only send one instruction per day. The headlights no longer matter. The fuel is slowly running out, and the road itself is invisible. Yet the car is still reporting road texture, traffic conditions, and weather from farther away than any traveler has ever gone. That is Voyager 1, minus the part where any road trip ends somewhere familiar. The spacecraft has also contributed to something subtler, public understanding of what exploration really is. Exploration is often imagined as a sequence of dramatic arrivals. A ship reaches a continent. A rover crests a ridge. A telescope images a galaxy. Voyager's later life has been different. It has turned exploration into endurance, patience, and the ability to infer meaning from whispers. It reminds us that frontiers are not always spectacular at first glance. Sometimes they are discovered in changes of percentage points, in the frequencies of plasma oscillations, in the fact that the background particle population is no longer the one you knew before. That requires trust. Trust in instruments, trust in physics, trust that the universe is intelligible even when it is not visually dramatic. And the universe, through Voyager, has rewarded that trust. For example, one of the elegant surprises from Voyager's interstellar measurements is that the plasma density beyond the heliopause appears to increase farther from the Sun, in ways linked to passing shocks and compression regions. These details matter because they allow researchers to study how disturbances propagate through the local interstellar medium, and how the heliopause behaves as a boundary. Again, this is not just local trivia. It feeds into broader astrophysics, how stellar winds shape their environments, how cosmic rays are modulated, and how planetary systems may be shielded or exposed depending on the properties of their host stars and galactic neighborhoods. If you step back far enough, Voyager 1 is part of the science of habitability, not directly in the sense of finding life, but in the deeper sense of understanding the environmental envelope around a star system. A strong astrosphere may reduce some galactic cosmic ray exposure to planets. A weak one may not. The interplay between star, plasma, magnetic field, bromsim, and interstellar medium shapes the radiation conditions of worlds. We are only beginning to understand these relationships, and Voyager gave us the first direct crossing point from theory into measurement. There is also the issue of memory, and not just the spacecraft's memory chips. Voyager 1 is a memory of a certain human attitude toward the future. It was built in an era when engineers were willing to send hardware on journeys expected to last years, and then keep listening for decades. Its systems reflect a confidence that careful design could outlive trends, administrations, and even some of the people who created it. Many of those original engineers are gone now or long retired, yet the machine persists. New generations inherit the conversation. That continuity is rare. It is deeply moving, and it is scientifically priceless. The deep space network operators who track Voyager today are part of a chain of stewardship stretching back nearly half a century. So are the scientists interpreting the data and the engineers keeping the spacecraft functional against absurd odds. Voyager 1 is not just transmitting plasma measurements and particle counts. It is transmitting an obligation across generations. Keep listening. Keep learning. Do not let the line go silent too soon. If you want one especially striking image of what that means, consider this. When Voyager 1 sends a signal toward Earth, that radio transmission leaves a spacecraft in interstellar space and travels for nearly a day across the black, passing the outer realms of the solar system, crossing the orbits of the giant planets far inside its path, and sweeping across the inner solar system, reaching Earth and being caught by a dish on a rotating planet crowded with noise. Somewhere, buried inside that vanishingly weak ripple, is a report on the density of plasma between the stars or the temperature of a spacecraft component built decades ago. Human beings extract meaning from it. Then they speak back into the dark. That is one of the most astonishing ordinary things our species does. It is also worth remembering what Voyager 1 does not tell us, because scientific honesty matters here. It is not giving us high-resolution maps of interstellar clouds. It is not detecting alien civilizations. It is not photographing unknown planets in the dark. It is one spacecraft on one trajectory with limited surviving instruments. Its data are local, specific, and constrained. Mohan, we must not inflate that into fantasies. But the truth, even constrained, is powerful enough. Voyager 1 gives us direct local measurements from a region no other functioning spacecraft had entered before it. It tests our models with reality. It shows us that the edge of the sun's influence is both tangible and complicated. It reveals that interstellar space is not empty silence, but structured plasma, threaded with magnetic fields and energetic particles. And it proves that a fragile machine from Earth can remain scientifically useful at distances once reserved for pure imagination. There is another subtle lesson hidden in its transmissions. Distance does not simply weaken things. Sometimes it clarifies them. Close to the sun, the solar environment is loud. The solar wind dominates. The heliosphere shields and shapes the particle environment. Oh yeah, beyond the heliopause, some of those local effects fall away, and the broader galactic environment becomes clearer. By going farther, Voyager 1 is not just escaping home. It is allowing us to distinguish home from what lies beyond it. It turns the solar system from a universal default into one region among many. That is intellectually profound. The conditions we live in are not the background setting of reality. They are the local weather around one star. This is part of why the mission feels emotionally larger than its hardware. Voyager 1 physically reduces Earth and the inner solar system to something provincial, not in a humiliating way, but in a clarifying way. We live inside a bubble blown by our star. We once thought of the planets as the whole system. Then we learned about heliospheres, Kuiper belt objects, Oort cloud models, and local interstellar clouds, galactic magnetic fields. The map kept widening. Voyager 1 is one of the reasons it widened from abstraction into something tactile, and still it goes on. At nearly 24 billion kilometers, Voyager 1 is not racing toward a dramatic destination. It is entering a long aftermath. There will be no close flyby, no orbital insertion, no touchdown. Its mission now is pure passage. Drift, measure, transmit, endure. That simplicity is almost severe. It strips exploration down to its barest essence. Go farther. See how the environment changes. Report until you cannot. There is beauty in that austerity. It also forces us to confront how little of the universe we directly inhabit. Earth feels large to us because it is our scale. The distance to the moon feels vast because it defies everyday experience. The outer planets already stretch human intuition. But Voyager 1 has spent decades showing that even the great planetary realm is still just the inner district of a much larger stellar territory. And now, beyond that territory's plasma frontier, it has begun to show us how tiny even a stellar bubble is inside a galaxy. The Milky Way is about 100,000 light-years across. Voyager 1 travels less than a light day from us in almost half a century of flight. Put differently, it has gone fantastically far by human standards and almost nowhere by galactic standards. Both statements are true at the same time. That is not a contradiction. It is the universe teaching scale the hard way. And perhaps that is why Voyager 1 resonates so deeply. It is a machine of contradictions that all happen to be true. It is ancient hardware doing cutting-edge science. It is very fast and unbearably slow. It is leaving the sun and still feeling the sun. It is physically tiny and conceptually enormous. It is mostly transmitting numbers, yet those numbers carry some of the most emotional weight in all of exploration. Because behind every telemetry frame and plasma reading is the same astonishing fact. We built something that reached the frontier of interstellar space and kept talking. The wider meaning of that is not simply technological pride. It is that the universe becomes understandable, not all at once, but through patient extensions of attention. Voyager 1 is a long, thin extension of human curiosity, stretched so far that even light needs almost a day to bring its answer home. It tells us that reality is richer than our first intuitions, that boundaries we imagine as empty are full of structure, and that the space between stars is not a blank backdrop, but an active environment with its own physics. It also tells us something humbling about civilization. For all our noise, conflict, distraction, and short-term thinking, we are still capable of making tools that outlast eras and keep faith with questions bigger than a human lifetime. Voyager 1 is one of those tools. Its survival is not magic. It is engineering, physics, disciplined care, and decades of people refusing to stop listening. That makes its signal feel not only scientific, but human in the best sense. And perhaps the most haunting part is this. One day, Voyager 1 will fall silent, but the place it revealed will remain. The heliopause will still mark the breathing edge of the sun's influence. Interstellar plasma will still carry waves and fields through the dark. Cosmic rays will still move through the galaxy. The universe will not notice the silence. We will. Because for a brief span in cosmic time, a small machine crossed a boundary no species from Earth had ever crossed before, and it sent word back. So when you picture Voyager 1 now, do not imagine a heroic ship streaking through bright nebulae. Imagine a cold, aging spacecraft in immense darkness, dish pointed faithfully home, power fade-in by degrees, instruments listening to the almost nothing between the stars. Imagine Earth turning under its radio dishes, straining to hear. And imagine that from nearly 24 billion kilometers away, across almost a full day of light travel time, that tiny craft is still transmitting the shape of the frontier. Thank you for watching. If you enjoyed this, I would love to know where in the world you are listening from, and what message you would send into interstellar space if you had the chance. And for now, somewhere far beyond the planets, Voyager 1 is still whispering, and against all reasonable odds, we can still hear it.